number 10. Today we're going to answer the question, how does the loss factor affect generated voltage on a piezo? So basically the question is, we apply a force to piezo, then the frequency of the question, pertaining to the question wasn't asked, so I'll go ahead and talk about both resonance and also static application of forces. But before we get into what the answer is, how does force relate in the generated voltage, and this is probably speaking about either it's going to be a sensor application or an energy harvesting application. How does the loss factor play in to these situations? So first, I'm going to explain the origin of the loss factor. So here we have two grains, which is the sort of squiggly lines here, and within each domain, in each grain of a piezo ceramic, and probably almost 99% of the conversation that I do, if it's nuanced, it's going to be nuanced to PZT material, which is the most commonly used commercial piezo material. So you see these arrows inside, and you see these sort of rectangular, perpendicular boundaries. So each one of these boundaries contains an arrow, and that arrow represents a polarization direction. So a grain in a piezoelectric material contains different units of polarization, different domains as it's called, which is kind of apt for the name. It contains different domains which have unique polarization orientations, which are in the permissible kind of directions for a piezoelectric material, specific to PZT or whatever material system or class you're speaking about. So these walls or boundaries can actually shift and change. So if we take a very simple tetragonal, which is basically a rectangular kind of box-shaped crystal structure, if you have domains oriented in a certain direction, you'll have obviously displacement of positive negative charge, so it'll be kind of longer in the dimension where there's displacement. So the change in the growth of each of these domains, kind of absorbing their boundary atomic cells or unit cells of the crystal structure, that also adds a huge contribution to ferroelectric material properties, and PZT included. So the domains, they move and they add and then one section grows larger or smaller, and that adds to the piezoelectric effect. But it's also a lossy process. So there are losses, a significant amount of losses associated with this movement. So there's both introduction of an improvement of material properties. For example, the piezoelectric charge increases as a result, charge constant increases as a result of domain wall motion. But there's also loss factors, which then come into play, which then start to become larger as these domains start to expand and move and change in shape, because there's a lot of irreversible processes associated with that domain wall movement. So the doping that we do to PZT materials also then changes the mobility of the domain wall, so therefore we get hard and soft materials based on how we dope the piezo ceramic when we're creating it. In other processing conditions, we can allow those domains to move more, or make a situation such that they are fixed, or they have less ability to change and move. So this is what ends up happening. So if we have high loss materials, we also then, in order to get high properties, we also end up getting high loss. And specifically, we're talking about a single material class, namely PZT. And the same thing is when we have a lower loss material, which is basically the hard material, we also have lower material properties. And I wrote this ER because they're not, the loss properties are the most variable properties you find. You'll find easily 10 orders of, 1 or even 2 orders of magnitude difference between material properties in just one material class PZT. However, you'll never find kind of that range of properties within real properties. For example, the piezoelectric charge coefficient, assuming the process is to make it is done correctly, or for example, the permittivity. You only found that huge range existing in loss properties, but they always scale. Like, you'll have a larger loss material, you're going to have larger properties. You're going to have a lower loss material, you're going to have lower properties, and that's after obviously the optimization of those materials in their processing conditions. I just want to get one more step in because we're one slide away from talking about how those loss factors are going to affect the generated voltage. So I just want to talk about loss factors and what they actually are. So the material properties that we're typically used to measuring, for example, if you're applying a voltage and you're measuring current or charge and you're calculating the permittivity, those amplitudes that you're measuring actually represent sort of an apparent material property, which I drew in an absolute value sign here. But you both have real material properties, so you have sort of an epsilon prime, which is representing the stored energy, and the epsilon double prime, which represents the loss energy, or the due to hysteresis. You don't follow the same curve up to the maximum point as down. I won't get into the very details, but you don't follow the same curve both ways. Therefore, you're going to have losses occurring, and those losses are represented by the imaginary material properties. Usually, we just measure the apparent property as well as the phase angle here, which represents a relationship between the two. If the loss property is small enough, I'm thinking to do this backward. This should be single prime. This should be double prime. Oh well, we'll keep going. So because this is the real axis, so this should be single prime. This will be double prime. So if these two are actually if this is actually very large in comparison to the real properties, the stored energy is pretty large in comparison to the lost, then the apparent and the real will be about the same. So getting that out of the picture here and discussing that, we'll now talk about what happens in static situation. So static situation, let's assume that we have two materials, one that has more losses, one that has less losses, but their apparent, or at least their real material properties, are the same. So they store the same energy on the same electric field or upon the same force. So if you have higher losses, but the thing is here, when you have higher losses, the apparent material property will be larger. So the material will appear to be stiffer. That's going to reduce the strain and also reduce the voltage. And as far as the resonance is concerned, if we have more losses in resonance, we'll have a lower amplitude. Losses are hugely important, and this is where the distinction between soft and hard PCT really matters, and upon which frequency or what kind of operation you're trying to use. In resonance, you are really relying on the amplification of energy in the system, or the increased storage of energy in the system, which is only possible due to having lower losses per cycle, and the ability to accumulate energy in a material or in a system. However, for off resonance, you're not continuously accumulating energy. Therefore, that loss is not going to provide such a dramatic impact. So for resonance applications, you will get much lower amplitude, much lower strain, and therefore you have a lower voltage. However, in the static situation, it's not really going to matter the amount of losses that you incur in order to produce voltage from an applied force. However, in a resonance application, it is going to have a very significant impact to the amount of voltage you can generate because of the amplitude generated from the applied force. So I hope you enjoyed this video. Please share this with your colleagues and friends. I'm presenting new content every single day. This is a daily show, weekends included. So I also look forward to, this is actually a question from one of the viewers in the comments, so I decided to answer it in its own video. I'd love to do more videos like this where I answer questions from viewers like you. That just makes the content all the more interesting, so I can answer the things that are actually on your mind. So my name is Dr. Shakani. Thanks for watching, and I look forward to seeing you tomorrow on the next episode, number 11.